At the end of the last section, we introduced the definition of a derivative, and we saw how we could use the definition of a derivative to come up with a formula for the derivative of a function by looking at the average rate of change over an arbitrary interval x to x plus h, and letting h go to 0, right? We're taking the limit as h goes to 0, right? And so we did several examples where we found the derivative of a function using the definition of the derivative. But in general, we don't want to have to use the definition of the derivative every time we want to take the derivative of a function. So mathematicians have come up with formulas for general classifications of functions so that we don't have to go through that hard work of using the definition of the derivative and doing all that algebra, simplifying and coming up with a formula. All right, so that's what we're going to look at today. We're going to look at some formulas for different types of functions or combinations of functions. And then we can, once we have those general formulas, we can apply them to lots of different functions. All right, so first thing we're going to look at is what is the derivative of a constant function? All right, so let's see, what does a constant function look like? If I graph a constant function, in this case we have f of x equals k, right? So this is just essentially if y is f of x, then we just want y equals k. So I'm just going to draw a little set of axes here, and so if I graph the function f of x equals k, right, it's the y value is f of x, and so the y value is always the same for any x value. So the function f of x equals k is just a horizontal line, right? Horizontal line. Okay. Now remember that the derivative is the instantaneous rate of change of the function, or it's the slope of a tangent line to the function. So what is the rate of change of this constant function? Well, the rise over run, right, of this function is there's no rise, it's all run. So the slope is 0. Slope equals 0, right? And that is the instantaneous rate of change. It's the average rate of change. If you pick any 2 points on this line, the slope is going to be 0 between those 2 points. Average rate of change between any 2 points is 0, and the instantaneous rate of change is also 0. So if we have a constant function, then f prime of x, right, which is, I'll write it as d dx of the function k, which is just a constant, is equal to 0. All right, so that's pretty straightforward. And the next one too is pretty straightforward, the derivative of a linear function. So again, a linear function, the general form is y equals mx plus b, right? So I can graph what that looks like. It's just a line that crosses the y-axis at b and has a slope of m, right? So this is y equals mx plus b. So if we recall that the derivative is the instantaneous rate of change, or it's the slope of a tangent line. If I drew a tangent line to any point on this line, the tangent line would be the line, right? It would be the same as the line. And we know that the slope of this line is m. So we can say that the derivative, if I have, let's say, f prime of x, is the derivative of d dx of mx plus b, right, is just going to be m. Right? We can reason that out just from the fact that the average rate of change between any 2 points on a line is always going to be the same. And so the instantaneous rate of change is going to be the same, and the derivative is the same anywhere on this line. It's always a constant m, whatever the slope is. So now we could also do this with the definition of the derivative if we want to. We could say that f prime of x is equal to the limit as h goes to 0 of, and we can take f of x plus h. So we can do m times x plus h, right? We're just replacing x with x plus h plus b. And then we subtract mx plus b. And we divide all of that by h. Okay, so we have to do a little algebra, but and I don't know if this is really all that necessary because it's pretty reasonable that you're going to get m, but let's just do it as an exercise. Okay, so I'm just distributing the m plus b, and then minus. I'm going to distribute the minus, the negative minus b. And then you can see that we have some things that cancel, right? This mx will cancel with the mx, and the b will cancel with the b. And so we end up with the limit as h goes to, whoops, why am I writing infinity? 0, right? 0, it should be 0. H is going to 0. H is the interval width. And so I get mh over h. We can cancel common factors, and we just get m. So either way, we can use the definition of the derivative to show that for a line with a general equation, y equals mx plus b has a derivative of a constant m. Okay, so the derivative of a line is a constant. It's the slope. All right. Well, that takes care of the two of the most basic types of functions. And in the next video, we'll talk about power functions.